Module 1. The transmitter is the power plant. Module objectives. At the end of this module, you will be able to explain the importance of alternating current, describe what causes signal distortion, identify how the path of least resistance affects the signal and how to change it. The transmitter equals the power plant. What does a power plant do? It produces alternating current. Just like a power plant, the electromagnetic pipe and cable locator's transmitter creates alternating current. The transmitter is the most important part of the locating instrument because any changes made to the signal must be made at the transmitter. Once it's applied by our transmitter to the metallic utility, alternating current travels in two directions. Current flows away on a metal conductor and returns through the earth just like a power plant. Whatever amount of current leaves must come back to the transmitter to complete the circuit. Alternating current builds a magnetic field our receiver can detect. As locators, we call this magnetic field our signal. Current that's been applied to a magnet creates an electromagnet. The positive and negative poles switch and reverse. However many times those poles reverse in 1 second equals the frequency. Once applied to a wire, pipe, or cable, magnetic fields want to be round. The magnetic field expands as current flows away from the transmitter, and the field collapses as it returns back to the transmitter to complete the circuit. However many times that fields expand and contract equals the frequency. Magnetic fields attract. Any metal in the vicinity of the magnetic field will assume the properties of that magnetic field, thereby building its own. These magnetic fields then compete and disrupt each other. Any nearby metal will cause signal distortion and can lead to an inaccurate locate. In this example, the positive and negative fields are attracting to one another between the bar magnets. This occurs when current travels away on one conductor, positive, and returns on another conductor, negative. Magnetic fields also repel. In this example, the negative fields are repelling each other, like poles repel. This occurs when current is traveling the same direction on two conductors. Magnetic field distortion. In this example of an attracting field scenario, the highest potential signal could possibly be seen at 3 points, A, B, and C. That could lead to inaccurate locates. The locator will need to take appropriate troubleshooting steps to ensure an accurate locate once this issue is identified. In this example of a repelling field scenario, the highest signal could possibly be seen at 2 points, A and B, and could also lead to an inaccurate locate. The locator will need to take appropriate troubleshooting steps to ensure an accurate locate once the issue is identified. In this example of an attracting field scenario, the picture at the top shows the magnetic field if there is no other metallic utilities nearby. The signal shape would be round. The picture on the bottom shows what can happen if there is another utility line present near the target line. The signal shape would be not round. Distortion occurs anytime the signal is present near other metal. In either of these scenarios, peak and null would not agree. We will discuss peak and null in Module 3. In this example of a repelling field scenario, the picture at the top shows the magnetic field if there is no other metal nearby. The signal shape would also be round. No distortion would be present. The picture on the bottom shows what can happen if there is another utility line present near the target line. The signal shape would be not round. Distortion occurs anytime the signal is present near other metal. This could be anything metallic. Could be a car parked on top of the utility line, a dumpster that's there temporarily, a building, overhead conductors, any metal near our line could cause distortion. In this example, peak and null would also not agree. We will discuss that in Module 3. The path of least resistance. Current will always follow the path of least resistance. What is the path of least resistance? Simply put, it is the route the transmitter's energy follows in order to return to the transmitter. Example A shows current flowing towards the grounding point to the left of the T. Current does not flow to the right of the T due to higher resistance. Example B shows current flowing to the left and the right of the T. This is because there are two grounding points on either side. The path of least resistance can change. Current will want to flow towards the larger section of steel or towards the addition or subtraction and quality of the grounds. What is resistance? The opposition to current flow. Whatever amount of energy leaves our transmitter must come back to the transmitter to complete the circuit. As locators, we are constantly building a circuit and troubleshooting that circuit. Our signal will always follow the path of least resistance to return back to the transmitter. The bad news is, this may not always be our target line. The good news? We might be able to change the path of least resistance to work in our favor. By temporarily adding or removing a far-end ground, may pull some of the signal to where we want it to go. By adding a short jumper and another ground rod, we may be able to pull some of that transmitter's energy to the right of the T in order to complete the locate. Another option might be to completely change our hookup point to be further upstream. The path of least resistance will generally pull your signal to the larger chunk of steel, an anode, or towards the nearest ground. It is best practice not to try to fight the tides, but rather let the path of least resistance work in our favor by allowing it to pull our current downstream. You should now be able to explain the importance of alternating current, describe what causes signal distortion, identify how the path of least resistance affects the signal, and how to change it.